Dear students, greetings of the day. In today's lecture, we will discuss some important definitions, then Abel's identity, and deduction of Euler summation formula from Abel's identity.
Thank you.
Abel's identity. Statement: for any arithmetical function an, let capital Ax is defined by summation n less than equal to x an, where we assume capital Ax 0 if x strictly less than 1, if f has continuous derivatives on the interval y to x, where 0 less than y less than x, then the result of Abel's identity is y less than n less than equal to x en fn capital Ax fx capital Ay fy y to x at f dash t dt. Proof: let k is equal to greatest integer of x and small m is equal to greatest integer of y. Now, as per the definition of capital Ax, and capital A is 0 for x less than 1, that means the values of capital A same for capital K and this k and small x, because the only difference of these two is the fractional part. So by this, capital Ax is equal to a of k and capital An minus 1, and here, and opening the first summation for the last term, we are left with this and this, which are of opposite signs, so we are left with an only. So that means an equals an minus capital An minus 1, that we have used here. Now separating the summation into two terms, n from m plus 1 to k an fn summation n from m plus 1 to k an minus 1 fn. Which may again be rearranged in the form first summation as it is n from m to k minus 1 an fn plus 1. What we have done here is we have just substituted n minus 1 as n. So now we try to make two summations equal. For that, we will expand this summation for its last term and second summation for its first term. So we are left with n from m plus 1 to k minus 1, an common, fn minus fn plus 1, and the last term of this is ak fk, and the first term of this summation is minus am fm plus 1. Now we convert this into its integral, which is of the form n from m plus 1 to k minus 1 an and remaining terms as it is am fm plus 1. Further, again the first term as it is, and we will write an inside at f dash t dt plus ak fk minus am fm plus 1, because for t lies in n and n plus 1, at equals am. So that's why we have taken an inside the integral. Further, now we will add two integrals and subtract two integrals. So this may be written as minus, we apply the summation, so we will again rewrite this m plus 1 to k at f dash t dt plus ak fk k2x at f dash t dt minus plus y2 m plus 1 f dash t at dt minus am fm plus 1 minus k2x at f dash t dt y2 m plus 1 at f dash t dt. Now we will solve them separately. First integral is k2x at f dash t dt, as between k and x the value of capital AT is same, it will remain same, the integral value, that is k is the integral part of x, so this is ak times k2x f dash t dt. So we can easily solve this integral and putting the values of limits, so it becomes ak fx minus ak fk. Also the second integral y2 m plus 1 at f dash t be written as, again here between y and m plus 1, y and m plus 1, so at equals am, which is constant, so taken out of the integral, y2 m plus 1 f dash t dt. So again solving this integral and putting the values of limits, am f of m plus 1 minus am f of y. So now we will number these systems. So we will mark this as 1 and this 2, 3. So using 2 and 3 in 1, y less than n less than equal to x, an fn equals m plus 1 to k atf dash t dt plus axfx minus k2x atf dash t dt ayfy y to m plus 1 atf dash t dt y to m plus 1 atf dash t dt which may further be written as minus y2 m plus 1 atf dash t dt m plus 1 to k atf dash t dt minus k2x atf dash t dt plus ax fx ay fy, which may again be written as ax fx ay fy minus. So using the again the formula of definite integral, so that is y to m plus 1 m plus 1 to k and k to x, so it becomes minus y to x at f dash t dt, hence proved.